So Marcus is nodding. That probably means it works. Yeah, thank you very much for the invitation to speak here. I'm talking about Project VD, which started out as a one-man learning project for Lean and was really never meant to see the limelight. What I will talk about is value distribution theory. What are even like the objects that we are discussing? Maybe why is this mathematically interesting and why would anybody try to formalize it? Explain where the project has gone so far, and then mention one design decision and come out with a long and complicated wish list for MathLab. I know that Christmas is already gone, but maybe there are people here interested in discussing this or is setting up another workshop. Or maybe someone will tell me they already did it and I don't have to do anything anymore. That wouldn't be so bad. So value distribution theory is an old theory that talks about complex analytic and meromorphic functions. And for simplicity, here in this project, I consider only functions going from the complex plane to the complex plane. Right, and the goal is to develop, understand, and make use of a quantitative measure for the complexity of these functions. Methods is classical analysis. And let me go into a little bit more detail here. So objects are complex analytic and meromorphic functions. Not sure everybody's familiar here with this because we see people from many different fields. So complex analytic is given by a power series, and meromorphic means, in addition, it can have poles. So think of polynomial, the exponential function or sine, they're all given by a power series. And if you want to have poles, then you can take the quotient of two polynomials. You can take 1 over sine, but you cannot take sine of 1 over x because as you approach 0, this wiggles uncontrollably, and this is not a pole. What you could be taking instead is maybe a Riemann zeta function, gamma function, and many of the classical functions that have some name, some other name, dash zeta function. They would all fall into this category. Right. I should say something about quantitative measure for the complexity of functions. This is, of course, more tricky. Maybe I just do a few very simple remarks. We are working over the complex numbers, so polynomials are either constant or surjective. This is the main theorem of algebra. Sine is a very different beast. It's surjective, but it has infinitely many zeros. Polynomials have only finitely many zeros, unless they're constantly zero. The exponential function has no zeros at all, but other than 0, it takes any other number. So any complex number non-zero has a logarithm, has many actually. And the growth rate is, however, markedly different from the growth rate that we see of polynomials. And then there's Picard's little theorem that basically tells us that if a complex analytic function, like the exponential function, misses one point in the complex plane, but then the image also misses another point, then it's constant. And in a sense, value distribution theory is all about developing a quantitative version of Picard's little theorem. Measure complexity of functions by taking into account how what values they take, how often they take it, whether they take it infinitely many often or only finitely many, and the density of points where values are taken, like the density of zeros. Like for sine, it's evenly spaced, but it could become like denser as you go to infinity. This is measured, and this is measured in comparison with the growth rate, and this gives the quantitative measure for complexity. Why anybody wants that, I will mention in a few minutes from here. But first, methods. Methods are analysis in the style of the 1890s. So it's all classic analysis in a single complex variable. It can be done if you teach it in class, essentially as a follow-up course to the classic single complex variable 101 that we teach in the bachelor or very early in the master's program. So classic analysis, single complex variable, harmonic functions as well. There's a lot of contour integration, circle integrals in the complex plane, and then estimates built out of this using mean value property of harmonic functions. And for me, this is also why I started with Project VD as my first project, because I thought this is something I can do without knowing too much about Lean, because I don't need to develop complicated notions. All I need is complex functions, complex numbers, and integrals, and those were already in place. So that made it a very good starting project for me. But besides, why does anybody care about a theorem or a theory that has seen its prime days in the 1890s, which is almost like 150 years from now? And the answer is, well, it got a bit out of style until Paul Vojta developed a very striking analogy between Diophantine geometry that studies rational points in solution sets of polynomial equations and systems of polynomial equations. So a correspondence between that and value distribution theory. So to cut a long story short, Diophantine geometry asks, what can we say about rational solutions of sets of polynomial equations? We know that on the circle, there are infinitely many points that have rational coordinates. As soon as you start to look at anything more complicated than a circle, then you have few rational points or maybe none. And same holds in higher complexity for higher dimensional spaces like surfaces cut out in free space by polynomials and systems of polynomial equations. Complex geometry, the hyperbolicity section of complex geometry asks a similar thing. You have the same solution set, circles, higher dimensional spaces, obviously over the complex numbers, not over the reals. And you ask for holomorphic mappings from the complex plane into your solution set. So we know that the circle comes from or is built from the real line by wrapping up all points that differ only by an integer multiple of 2 pi. So we parameterize the circle by the real line via its angle. The same way you can build maps from C, the complex plane, into a tori, and higher dimensional tori, and then maybe you can even come up with a 2-dimensional torus where you have a 1-dimensional curve that is even dense, and complex geometry and hyperbolicity studies that. So in Diophantine geometry, one of the relevant quantities that you study when you study points that satisfy your equations and have rational coordinates is height. That's a quantitative measure for the complexity of the rational numbers that appear in the coordinates of that point. And in hyperbolicity and complex geometry, you have the Nevanlinna characteristic that is a quantitative measure for the complexity of the curve. And Paul Vojta noted that these two quantities, the height that we have in Diophantine geometry and the Nevanlinna characteristic that we have in complex geometry, they basically follow the same rules. The analogy, as far as I understand, is an analogy that's not as strict as an equivalence of categories or something. It's more like the analogy that you have between theoretical thermodynamics and information theory, where you have on either side a notion of entropy that basically plays by the same formal rules. And that is also true in the Vojta analogy. And then, of course, there's a whole subject of mathematics that takes problems you might have in Diophantine geometry, and maybe you're not able to solve them, then you ask, what is the equivalent problem in complex analysis, and let's study that. And whenever you have a conjecture on one side, then you might try it on the other side and see what you can learn from there. And this has meanwhile developed into a whole field. Maybe that's as much as I would like to say. Anything else would probably get extremely technical in no time at all. So maybe I should then instead present where we are. So what have we formalized so far? It's the first main theorem of value distribution theory. Value distribution theory has three main theorems. The first main, the lemma and log derivatives, and the second main. The first main, to formalize this, that basically the first main theorem speaks about the Nevanlinna height, the quantitative measure for complexity, and shows that this measure is invariant under certain transformations of the functions. For experts, it's the SL2 action on the P1, which is the image set of the meromorphic map. And in order to formalize this, we had to establish a lot of API for meromorphic functions. Meromorphic functions were already in place, but much of the API was missing. When we started this, the Laplace operator wasn't in MATLAB, so we had to add that, and API and basics about harmonic functions and how harmonic functions relate to analytic functions, that they're as soon as your domain is simply connected, then a function is harmonic if it's the real part of an analytic function. And of course, the mean value property. Then there was a lot of work on circle integration of special functions. In particular, one of the functions that is of constant interest in the theory is when you take a meromorphic one, then you take the norm of this function and log of this. This is almost everywhere harmonic, except where you have poles and zeros. There it gets interesting. And we need to do contour integration for this. And obviously, we had to establish the fact that these things are even integrable. And that was a lot of work. And I learned the hard way that doing actual computations in Lean is hard. Right, then the first main theorem, and finally, which took almost as long as formalizing it, is getting it into MATLAB past the reviewers. And maybe I should take the chance and thank the reviewers at this point for their incredible patience with a bloody beginner who was constantly getting on their nerves. At present, it's teaching time, but the semester break is coming up, and then a forward peek to the semester break is there are some classical formulas, mostly established by Elie Cartan, that describe the Nevanlinna characteristic, and this could be useful by some other groups working on a material related to Riemann zeta functions. Right. One of the first applications that you could do with value distribution theory is results for a transcendence of meromorphic functions. You have a bunch of meromorphic functions, then you have a new one, and you ask yourself, is the new one really an algebraic product of the old ones, maybe involving a few square roots and stuff, or is it really transcendental? And value distribution theory can answer that sometimes, and this is now within reach. Future is, well, there's the two other main theorems of Nevanlinna theory. Basically, the scope and size and the effort required to formalize them will be comparable to the first main theorem, I guess. So I would expect that the effort is about the same. So that's where we are at the moment. And then finally, I would like to discuss a bit some or share some thoughts about the MathLab, some design decisions that were taken, some design decisions that I believe are pending, and where ideally I would like to start a discussion because I feel that there are so many branches of mathematics that might depend on these decisions that I don't have enough of an overlook to be sure what needs to be done. So let's start with the simplest thing. The simplest design decisions that was probably mostly taken before Project VD came into play is the notion of a meromorphic function. If you open any book on meromorphic functions, and the way we teach it in class is we constantly say that meromorphic functions form a field. Simply because if you have meromorphic functions are functions with poles, and if you take the quotient of them, again, you have a pole, or so we think. And then without further ado, we use all those notions that are associated with fields, field extensions, algebraic, finite, transcendence degree, and whatever notion there is, we just use it. Trouble is, meromorphic functions do not form a field in Lean. And the solution has a tendency to become rather messy. So why do meromorphic functions do not form a field? This is super easy, because if you take the identity function x goes to x divided by itself, then it's not 1 that comes out. It's a function that is almost everywhere 1 except at point 0, because 0 divided by 0 in Lean is defined to be 0. So the quotient on the left-hand side is a non-continuous function that's almost everywhere 1, but not at that point. Of course, you could try to fix the problem by defining, okay, let's maybe change the definition 0 by 0. We define it to be 1, but honestly, that I don't think this is going to help. This will just make matters worse. As obviously, you can play the same trick with sine and cosine and immediately come out with a function that's 1 almost everywhere and is discontinuous zeros along a discrete set. Right. And soon it becomes clear that when we say meromorphic functions form a field, we're not talking about meromorphic functions. We're talking about meromorphic functions modulo codiscrete within. So modulo, what is this? Eventual equality according to the filter codiscrete within. So we identify the function 1 with a function 1 that has a discontinuity at 0, or that has a discontinuity at every discrete set. So maybe we should have taken this as a definition of a meromorphic function, but then again, we have new problems. The quotient map is a ring morphism. So if you have an honest meromorphic function and you map it to the meromorphic functions modulo that relation, that's very nice. Obviously, when you have the function that's almost everywhere zero and has a few discontinuities, you can do continuous extension. And that is, if you wish, a section from the quotient set, which is a field, into the meromorphic functions again. However, that is not a ring morphism, and then all problems come along. And of course, similar problems if you say, okay, a meromorphic function is an element of the quotient. You could do this, change the definition, but then you want to do contour integration, and contour integration you can do if you have a function. If you have an element of the quotient, you can take a representative, well-defined up to modifications on a discrete set, and you can say that discrete sets, they don't come into play when I do contour integration anyways, except if the path that you integrate over is a constant. Then it could lie exactly in the discontinuity, and you don't get a nice theory out of this. So my feeling is one way or the other, it's going to be messy, and we have to live with this. And probably the only sane solution is to discuss meromorphic functions on one side and have a new notion for the quotient that is a field and where all the field theory applies. So that was one thing. In a sense, this design decision was already taken when people defined or introduced meromorphic functions to MathLib. Maybe looking a bit into the future, one of the key notions that I think is missing from MathLib is a differential operator. Differential operator come up all over mathematics, certainly in Project VD. But how to define them, I'm unsure. I am sure, however, that if you make a mistake defining them, then Hell's Gate will open and we'll be in a lot of trouble. So differential operators show up everywhere. We have line derivatives of functions, which I believe in MathLib are a bit of a second-class citizen. We definitely want to not only line derivatives, but Lie derivatives, so derive functions not in one direction everywhere, but according to a vector field where the direction that I differentiate into will change from space to space. Then also we don't want to derive just functions, but also differential forms and probably pretty much any tensors. Differential forms are at the moment avoided in Project VD, and some of the code that we have there is actually working around differential forms. So we don't have to use them because I couldn't see them in a convenient place in MathLab. Then certainly if you do complex analysis and certainly if you start to do higher dimensional things, you have del bar and harmonic functions we introduce. So the Laplace operator is also a differential operator. And sure, we are going to have much more of this if, I mean, one obvious project in MathLab that should be addressed now or started is Hodge decomposition for compact Riemann manifolds. This is all about differential operators, so we need them. They also come up in algebra, in algebraic geometry, and it's not clear to me if we can have a definition that covers those two very different fields. And obviously, people study this over fields of positive characteristic in p-arting settings where I'm not enough of an expert to have an informed opinion, really. So if I go to the literature, then it seems to me the best definition is this. We have a space, maybe the complex plane, maybe your manifold or whatever. we have a sheaf of rings, we have two sheaves of modules, and sheaves of rings and modules are complicated beasts. So let me just say the sheaf of rings. This is the notion of saying smooth or analytic function, or maybe n times continuously differentiable. And f and g, they're functions, maybe they're differential forms of similar regularity. And then Grothendieck defines the differential operator as a map from functions to functions, or from functions to differential forms. And it's a differential operator of order 0 if it commutes with multiplication, so linear, and it's a differential operator of higher order if it satisfies some iterated Leibniz rule. So this is the definition, and this is a definition that I would very much like to see in MathLab. However, I'm unsure how well this plays with the tradition of MathLab to define or to give default values to things where an operation is not defined. So we have the derivative of a function that is non-derivable is defined to be 0. And here we probably want to take a differential operator, maybe of order n, and apply it to a function that's only n minus 1 times continuously differentiable. Or we might want to apply it to a function that's LP. And then what we have makes maybe sense only away from a 0 set. So much of the literature that I'm aware of, which is maybe not the whole literature, discusses these differential operators only in settings where you have infinite regularity. But you definitely want to take the Laplace operator times and again of a function that's not everywhere C2. And I could imagine that trying to formalize this could be a real challenge, and it needs to be given some serious thought. And as I said, my goal in this talk is to start a discussion and maybe get something started if all works out. And I understand my time is up. So thank you for staying with me.
Thank you, Stefan.